We are ready to start. Some thoughts about constraint sampling algorithms. Benedict Leimkuhler.
Okay, thank you. Yeah, I gave a talk in the satellite workshop up in Edinburgh less than a month ago, I guess. And so I knew there'd be some of the audience from there would be here as well. So I didn't want to duplicate everything that was in the talk. And also I want to talk a little bit more about constraints. But to say some of the things I will duplicate some of the slides from that talk. And this is very much work in progress, and particularly the applications that I'm going to describe at the end. Let me just start by saying a few words about sampling and molecular dynamics. This is introductory for this topic, but it's not exactly the topic of the Newton program, so it's probably worthwhile to mention these things. Sampling algorithms for me are just methods for computing averages, like this integral here, with respect to some probability measure with a density given in this way. For example, this is the Gibbs distribution. And there are lots of ways, of course, to sample a given probability distribution. When you're in high dimensions, you actually have relatively few options. Sort of MC methods become the methods of choice, and in particular things like HMC that we just heard about, but also methods based on discretization of stochastic differential equations, and that's the kind of schemes that I'm mostly working on. So this is like a Brownian dynamics, so the simplest SDE you can write down to do this sampling problem. And I want to talk about ergodicity issues, although we do have interest in things like ergodicity and properties of the SDEs themselves. We have recent papers on that, in particular in conjunction with the underdamped model. My battery might have just run out. Then if you have Brownian dynamics, in order to put it on a computer, you have to use a discretization scheme. And one of the common choices for that is the Euler-Maruyama method. And I'm going to mention that we have an alternative to that, okay, which is, we call it the Leimkuhler-Matthews method, so we name it after ourselves, which is a very simple change of the Euler-Maruyama method. It's quite worth saying this. If you haven't seen this scheme, it's a very simple modification in the sense that you don't have to change how you treat the forces. It's done as Euler's method. But in terms of the increment that you're introducing, the Gaussian increment, you now introduce a pair of Gaussian increments, and you just put them in this very simple form. It's just a sum here, an average of two successive increments. And what that means is that there's a correlation between the increment that you're using at each step. And this has fairly profound effects on the accuracy of this scheme for computing averages, for computing observables. So we've studied that quite a bit now, and we have several papers on it. So that scheme looks very strange from the point of view of SDE numerics. So when we introduced this, a lot of people asked us, so where does that come from? And actually the way we derived that scheme was by thinking about underdamped Langevin dynamics. So the case where you have momenta in the system as well. And then we looked at a high friction limit in underdamped dynamics in order to derive this method. And so we didn't have a good explanation for where it comes from, other than to say, you do it this way, and then it seems very obvious. Okay, so this is the underdamped model here, and I've indicated a splitting method. So the three parts are A, B, O here, and if you treat these, we've had talks on this in the sort of micro workshop we're having. So somehow splitting up the stochastic differential equations in this way, then you can build integrators by composition, just as you would symplectic integrators for Hamiltonian systems. So this is now a sort of tried and tested framework for building numerical methods. And what we did in that paper was to look at the Tale-Tubero expansions in terms of the ergodic properties, in terms of the invariant measure. And so using this kind of PDE technique, you could actually calculate the perturbations of the invariant distribution due to the numerical bias, okay, due to the discretization scheme that you're using. And we also could compare different schemes in terms of the marginal configurational bias. So somehow we have positions, momenta, we don't really care so much about the momenta. We integrate out over the momenta, we get configurational averages. And you could actually show how the bias in those configurational averages was affected by the choice of the integration scheme. So if we chose one scheme, we would get one formula for the bias and for the leading term in the bias and configurational quantities, and we get better results with other schemes. So it turned out that if we use the Bay-Oab splitting, which means take B, A, so the B step is just a kick, A, O, A, B, then the scheme was much more accurate. And you can see it here. So if you take so this is the overdamped equation at the top, and so if you treat that by discretization directly, and you look at the invariant measure that you obtain for the numerical method, you can compare it against the invariant measure for your original system, for your SDE, which is, of course, the Gibbs measure in this case. And then you can see that if you derive a scheme by taking the Obabo splitting and let the friction go to infinity, you derive the Euler-Maruyama method, okay, in this overdamped setting. And if you take the Bay-Oab scheme, you get this other method, okay? And this one has second order accuracy in the effective step size, as opposed to first order for Euler-Maruyama. So it's all very natural when you're working in this framework of underdamped equations, and then just take the high friction limit. You can see this difference in real applications.
Yeah, so usually when you do this kind of consistency analysis on ODEs, there is a counterpart which is stability, which may degrade. So here maybe you can come
No,
up
you
with
do
stability.
even better in stability too. You go right up to the theoretical threshold, which is defined actually by the deterministic equation. So really the methods work extremely well, and we've studied them pretty much to death at this point, because I think it's quite a nice property and we wanted to understand it fully. And we also want to understand its practical implications. So this is showing for a little molecular model how the error behaves. This is actually the exact same computational work using Euler-Maruyama or this scheme. So the constants that are appearing in the error formulas would be modest as well. So you're getting the higher order of accuracy, but you're also getting high accuracy, which is a little different thing. And you see this when you work with the underdamped model. Sometimes you can't let the friction go to infinity because it slows exploration of the landscape. So in many molecular systems, you actually have to work with an underdamped model, but we see these kinds of accuracy improvements, and there are other reasons actually that go into that, have to do with the exactness of these schemes for harmonic models and things like that. But I'm not going to go through all that. I'm just saying that there's some splittings that are much better than others, and this is a particular ordering of the pieces that gives you a really good result. So now I'm going to switch gears a little bit and talk about Bayesian inference statistics and a little bit about neural networks, very little. So of course, Thomas Bayes, I always have to mention that he was the first Edinburgh data scientist in 1721. Actually did it within theology, but it's a strange thing. Of course, that's about fitting statistical models to data. So you think of having some parameters, theta. This is the framework that we have here. So we have some data points. We have a statistical model involving parameters theta. We'd like to find the right parameters for the data that we have within that context of the statistical model we're using. And this gives you a formula for the posterior distribution of the parameters given the data in terms of a likelihood function, which is just the definition of the model. So you can apply something like that in, for example, binary classifications. You have some data points, and you're trying to find, in this case, you're just trying to find the orientation and the the position of a line which is separating these two data sets. So you can do it with that little neural network. That's about the simplest neural network that is useful for anything. And it's actually a really good toy problem for playing around with. So the ReLU is the rectified linear unit. And this is just it's a very simple, function which defines the activation. And then the sigma is a sigmoidal function. Of course, you can generalize that and make more complicated networks, so we've been studying those lately. Now, the way people train these networks is to use stochastic gradient descent. So this is like the most popular method. So I've written the gradient down there from the Bayesian perspective. And well, I should say, so the connection with molecular dynamics is just that if you take that problem in the Bayesian framework, then you again have a distribution function. You're actually trying to sample a probability distribution, and you can reinterpret it as a kind of a molecular problem. So that's a way to map molecular dynamics techniques into the applications in statistics. And so that's what we've been exploring and trying to find out where that works and where it doesn't. But the way people tend to treat this problem is just to take, so the gradient here of the loss function, loss is playing the role of an energy function. And well, because you're typically thinking of using these things in a setting where there's very large data sets, they do an approximation to the gradient. So you would just use gradient descent and try to find a minimum of this loss function. But instead, they truncate that gradient with just taking a random subsampling of the data points at each step. So every time they evaluate it, they're introducing some random perturbation, which is coming from the subsampling. And then if you do that and you just write down a numerical method based on that, you end up with something like this. Okay, so this looks like Euler's method, but now we have a stochastic gradient here. So really we should think of that as a stochastic map. And you can actually turn that into, I'm not going to go into all the details of this, but you can turn that into a SDE sort of working backwards. So you can think what we're really doing is applying Euler-Maruyama to a certain stochastic differential equation, and there it is. And some covariance here that you may not easily be able to get a handle on, which represents something about the way that you're doing your subsampling of the properties of your data set. This is actually slightly modified from what you would get directly from that. I've added this term sigma squared times the identity. And what that adds is a sort of regularizing effect. It was first used by Welling and Tay in their paper on stochastic gradient Langevin dynamics. So they introduced this additive noise term. And the reason is that if you don't do it, you have a degenerate problem, and it makes it actually very difficult to study. So this is a kind of a simple regularization of the problem by turning that degenerate noise into non-degenerate noise. And so they didn't have too much numerics in that paper, but a lot of people have used SGLD and found it to be useful. And so we picked up from there, and we've been trying to understand how we can improve on this idea. So we want to use additive thermal noise in order to enhance the exploration of the loss landscape. And one of the observations in this talk is that you really can think of just that procedure that you get by discretizing this with the Euler-Maruyama method, or some more sophisticated SDE discretization. You can think of it as a training strategy. And you can think of it as a training strategy without doing some of the things that are mentioned in the literature, such as taking the step sizes to 0 or driving the temperature down, like in an annealing strategy. You can just take the samples that are generated, and they're actually quite good optimizers themselves. So the point is just to use a low enough temperature, and the results are very good. And so there's some interesting things that we found from that study. So here's one example. I'll just show you a couple of examples. These are done with an app that we made to study 2D classification. So this is the Beoab-Langevin dynamics method with some particular parameters there. And tau, which is written above each of these panels, that's the temperature. So 10 to the minus 8, 10 to the minus 7, 10 to the minus 6, 10 to the minus 5. This is the same amount of computational work. And it's just showing that in this example, you're getting much higher test accuracies and you can just see the quality of the classifier. So that's shown by the contrast that you see here between the data points and the classifier, which is graphed in the background. It's generated by a neural network approximation. It's like 500 nodes, a single hidden layer perceptron. So it's a neural network that's constructed by just taking inputs into the hidden layer into output to the classification. So, but you can see that it improves here with the temperature.
Can you explain the colors again?
Well, they're just random. They're not completely random choices. This yellow points are on the blue background, blue points on the yellow background to show contrast. Otherwise, they get buried. Okay, so that's the color. And in between, it's just this is.
So the
you
blue
can think of
points
this like
should
the
be
confidence.
in the yellow contrast. The blue points are
Yeah,
the data.
exactly. These are properly classified here. These points because there is a high contrast.
Can you learn the temperature as well? Can you?
Yeah, well, that might be the next thing. We have some methods that we're studying with Eric van den Eyden on. It's called infinite swap simulated tempering. It's kind of a strategy for exploring many temperatures at once in one simulation. But I won't talk about that today. But there are methods for doing things just like that. Just to show you another example, this is spiral data. So this is quite tightly wound spiral data, and it's recognized as a fairly difficult classification problem when it's tightly wound like this. Okay, so this is usually a hard problem for neural networks, and so you need a few hundred nodes for this. But even with a few hundred nodes, sometimes it doesn't work too well. And SGD, for example, gets stuck on this problem. It's very hard to get it to work well. There are better optimizers than SGD, like Atom method, which is popular for this purpose. But here you can see, again, I'm just showing you the difference with temperatures. As we increase the temperature, there's kind of a band, like a Goldilocks zone, where the method's working well.
Tau, what is tau, the step size?
Tau is the temperature.
Okay, so you have to tell me what it is in the differential equation.
Tau is the temperature parameter. It's just scaling the noise.
Okay. Mm-hmm.
The additive noise.
Mm.
So here, the task that you are setting to do, so it would be like the middle one and the top is the one that's doing
These
the
ones
best.
are good. This is good, right?
This is good.
Because we're getting a high contrast. It means we're separating the points.
So you want to separate the blue and the yellow points.
Yeah, exactly. That's the classification task.
That's the task.
Yeah. So here it's all muddled together. So obviously not performing very well, and at high temperatures also, that this quickly become actually unstable at those high temperatures, or at least unstable in some parts. So here's some other pictures. This is showing for different numbers of actually nodes, not weights, 10, 20, 50, so these are in the hidden layer. And for different methods, so stochastic gradient descent, the method I mentioned, Atom, well, complicated method that people use, okay? And Langevin dynamics. And what we've been looking at lately is a lot about the parameterization of these methods and other methods as well. So how we can choose parameters of a stochastic differential equation in order to control properties of the classifier. We actually love to be able to prove theorems about that. Okay, so to prove something about the structure of the classifier, which is like, sort of, you can think of it like a phase field solution, you know, like in phase field models for PDEs. It's kind of like that, okay? We'd like to be able to say something about these solutions that we get in relation to the parameters that we're using in our SD model. And that's just for gamma equals 0.1. And well, what you see here is that somehow they're all giving fairly jagged classifiers. They're all sort of able to solve that problem.
So what is the reason why you get this straight line segment as border?
Well, each of those straight line segments is corresponding. This is a single hidden layer perceptron, so we have these nodes, and each one of them has two inputs, okay, x and y, and there's a line associated to the weights that are on that, and some of them are large and some of them are small. If you have a good distribution of those weights, you actually don't see these straight lines so strongly. They're pronounced when you have just a few weights that are exaggerated. And so this is probably due to having a large weight. Timothy Bouchon, who's working with me now, is actually studying that behavior. So this is just showing that when I change the friction coefficient, which is sort of arbitrary in Langevin in terms of the invariant distribution, it has a strong effect actually on the smoothness of these things. And we got very interested in that because I think that is very important for generalization and things like that, the kinds of things that neural networks people are very excited about. So we wanted to understand how to make smooth classifiers. And so that's ongoing work. I'm going to show you at the end of the talk a way of doing that. So these are results at a particular time. But one of the interesting things that you realize when you think about how these methods are made and about there's a sort of embedded symmetry group in the neural network that you can rescale the weights at different layers, okay, preserving the output, the loss function. So given that, it means you can sort of slop around in a kind of on this manifold defined by those associated with those scaling symmetry groups, which means you can actually have large weights sort of appearing and still have the same exact classifier solutions, or same classification quality. And it's actually the products of these weights that would be important in neural networks, because that will define somehow the steepness of these classifier boundaries. In this example, if I run Langevin dynamics for a very long time, these will steepen. And that's actually an interesting effect, so we're studying that. So I'm going to come back to that later.
What do you mean? Would steepen?
It will become, okay, so think of it like a phase field model, 0 here where it's like blue and 1 here. And so it's...
The interface would be more...
The interface
sharper.
becomes sharper,
The gradient
and
would be...
we think that's bad. In fact, that seems to lead to instability also of these training strategies. So many understood things. But that's just to show you that we can use Langevin dynamics to do this kind of training. In principle, it does things in a similar way in terms of the solutions that we get to the methods that are being used for neural network parameterization. So let's try some others. So these are all the kinds of schemes we've been working on in recent years. So these are all of our SDE-based methods, numerical methods, which handle different situations. And I mean, these are more or less applicable to these kinds of applications, but some of them are for special things like dissipative particle dynamics. Many of them are for general purpose configurational sampling, and so they can be used. And so what I've been looking at lately is how to use some of these techniques in order to enhance this whole training process. And one thing I'll mention is this, but I'm not going to go into the details of this, what I talked about last time in Edinburgh, this adaptive Langevin method. I'm going to say something about constrained Langevin techniques. But there are many other schemes that would potentially be useful in this context. So this is actually 4 methods now, SGD, Atom, Bayoab, and then look at this last one. I mean, everybody else is just getting out of the blocks, and it's already got a beautiful classifier. I think that's a beautiful classifier, by the way. And so there's something a bit special here going on. We're very interested in this. So this is something we call ADLALA, okay, which is a combination of adaptive Langevin with Langevin. And it's a partitioned method. So part of the system is being done with one method and part of the system with another. So you can think of just having different Langevin parameters in different layers, a simple version of this. And what you can see is that it seems to dramatically improve the convergence rate. So we're getting a very rapid convergence. And remember, we're never driving any temperatures to 0 here. So these are optimizers, but they're optimizers that are actually samplers. They're just low temperature samplers. I'm just going to show you again because it's such a lovely movie. Particularly concentrate on ADLALA. It's sort of magic the way it comes in. So obviously, if we could get this to work for lots of other applications, well, we might be famous. So, so that's obviously a goal.
What are the number of data points you're using in this?
Sorry?
How many data points are you more or less
I
using?
don't know. Tiffany, any idea?
1,000.
Something like that. Yeah. So,
So you said something that you're not driving the temperature to zero. So why is that?
because we're just at the bottom. We're at a low temperature point, but it's not the bottom. It's not the absolute bottom. We're down, in the valley. Yeah. So, but somehow the temperature is helping, and one possible reason for that comes from this Swansig theory of diffusion on rough landscapes, which is a kind of homogenization concept. But I'm not going to talk about that in front of people like Tony, so I know more about what I'm talking about. But let's talk about this instead. Okay. So this is now what I'm going to be talking about is constrained Langevin dynamics, which it's actually come up in this discussion here in these different talks. In particular, our geodesic integration approach to Langevin dynamics. And then I'm going to give an example at the end, which relates a little bit with this neural network stuff. So this is just a constrained model. We've seen this actually already here. So lambdas are Lagrange multipliers. These are algebraic constraints. This is the hidden constraint or the cotangent constraint. And this is the cotangent Bandolin. We want to do Langevin dynamics on this, so we have some noise introduced here and friction in the usual way. Okay. And
Crash course DIE stuff. Why do you need to invoke the constraints?
Well, you don't really, but it's quite nice to write it down because everything you're doing is really in this space. You actually want to preserve that manifold. And when you do a splitting method, it's actually quite important because you use this one in order to enforce to develop one part of the splitting. And so I think it's more complete to just.
Basically, that's the time derivative of the first constraint.
Yes, indeed. Yes, I mean, yes, I understand that, but. So this is the idea in this geodesic integrator paper. That's meant to be a diagram of a method, but it's not very clear what it is. It's supposed to actually compare two different methods, and you're supposed to understand everything from this picture. So, but shake is this method, this sort of classic method in literature for constraints, where you sort of take steps, you leave the manifold, then you project back to the manifold along a vector which is normal to the manifold at the start of the step. Okay, that's its basic structure. And the idea in this geodesic integrator is that you actually preserve the manifold during the whole evolution. Okay, so obviously it sounds weird. You're going to do just what you wanted to do, why you wanted an integrator in the first place was to do that, right? But there's some tricks at play because we don't kind of care that we have exactly the right evolution on the manifold. So we allow some error in that part. In particular, we allow that we aren't treating the forces continuously, right? So we're not actually solving the differential equations in the manifold exactly. So, and this stuff has already been introduced in other talks here, but so yeah, it goes back, our approach to it goes back to this paper with myself and George Patrick. Actually, what happened was I wrote down this method and sent it to Charlie, and I said, "This really looks good, but I'm sure I've seen this geodesic approach somewhere." It shows I'm really getting old. It turned out we done it for deterministic systems. We had done something very like this in this paper with George, and but the idea is we wanted really to extend. The whole point of this was to extend the Bailout method to constraint manifolds and get results that are similar. And we're kind of despairing because many people had actually tried this and put it into codes and said, oh, it's just not working. And we had tried some simple approaches to it, and they had also failed. So we just went back to sort of scratch, to start from scratch. And and drive the integrator just thinking, what would you like to do? Well, you'd like to break up the system and do B, A, O. Now, what is B? Well, you go back to the differential equations and you look at it, and you see, okay, B is going to be, I have the kick here, right, to the force, and then I just ignore all the other stuff. But I think of doing it so that I preserve the constraints. So I leave in Lagrange multipliers, and well, in this case, you'll want to use the cotangency constraint. So you want to then preserve that. You stay in the cotangent space during the B step. Then the O step is similar, right? It's the Ornstein-Uhlenbeck projected into the constraints. And what's the A?
You need the Lagrange multipliers in the O step.
Well, it's all linear. The transformations are linear. So there's no problem in the B and the O.
Okay, it stays anyway.
No,
Easy to implement.
No, I'm trying to understand.
it doesn't stay if you don't make it stay. So you have to do something, but it's just a linear projection. But the A step is the interesting one, because the A step, you have to actually follow the manifold geometry. But you think of it as like drift on the manifold, just free motion on the manifold, no forces. So that's a geodesic, right? That's just a geodesic path. So that's why I call this a geodesic integrator. We're just following geodesic paths for, for that A step. Okay, so we have,
Geodesic with respect to the kinetic energy of your problem. So the
with respect to
metric is
with respect to the manifold geometry in this case, which you could make a kinetic energy metric for that. Now, the big difference between this and the original problem is there's no F here. So in molecular dynamics, F is everything. That's the cost of the computational, measure of work, right? Is F. It's whatever it takes to compute F. Because you have long-range forces, you have very expensive force fields. The constraints, they're cheap. In molecular dynamics, it's like the bond stretches, maybe just the fast bond stretches, the ones to hydrogens from heavy atoms. It's really very small, dimensional, easy to solve. So the idea was we could do this with shake discretization. That's sort of the generic scheme here that you could use. Just apply shake to this, but there's no forces. So it's kind of multiple time stepping, if you know what that is. But it's one we're doing in this special way with the constraints. There are other ways you can treat this. So I'm going to show an example like this where you solve them analytically, and another one where you actually just solve it by simple splitting. Okay, so in some cases you can do it, and then it's really good to do it. I just mentioned, I've got to stop pretty soon, actually. I'm just going to mention for molecular dynamics, we used this together with yet another step. So we did another kind of sub-splitting to break up the system dynamics in order to make it allow us to get past a stability threshold that would appear due to angle bonds in solute molecules. So that's a little bit complicated to go into, but there's like one more layer of multiple time stepping that we inserted, which allowed us to take very large step sizes for molecules, for biomolecules. So biomolecules, typically, the step size is thought to be around 2 femtoseconds, if you ask practitioners. But the people who really work on integrators in the chemistry literature say you can go to about 4 femtoseconds by using a lot of tricks, shake and multiple time stepping techniques and things like that. It's difficult to get beyond 4 femtoseconds, or certainly beyond 5 femtoseconds. So what I'm going to show you is actually slightly breathtaking. This is going up to 8 femtoseconds with stability using these schemes. And it's a really simple method. So to be able to get here is actually not trivial. And just to illustrate that it's not trivial, Tony's method tops out at 4. So, the other one there is the Bucci-Parnello method. So that's another very popular Langevin integrator adapted to constraints. And actually we've adapted those using the best technique we could find, which was geodesic integration. So we made a geodesic version in order to prove it. And that's where we get to. But that's the Tinker one is something that's built into one of the codes. But here, with 4 femtoseconds, the accuracies are much, much higher. So this is the error in in the some computed quantity. In this case, it's an energy. So we have some papers on that, and we're trying now to. It's actually gone into OpenMM, which is a big code which is used in folding at home, and I'm told that that means that in the next version of folding at home, our code will be used. So that means it'll be used on, you know, I don't know, millions of computers around the world, because that's farmed out to PCs while people are sleeping and does computations for proteins. So it's kind of I think, an exciting method. Just to show you something very recent we did with this is a molecular dynamics with pressure. And we were trying to derive, again, an integrator for a complicated system now with just a kinetic energy as a function of position, so a little bit more complicated form than the usual sort of, you know, kinetic energy depending only on momenta and separated from positional potential energy. So, but you have to extend this system a little bit to model the box geometry, and then you can simulate. And the methods that we were trying to derive for that were failing. Okay, literally, we tried many schemes from the literature, and then our own ones, including one that Eric Benedict suggested. And so Anton, my PhD student, was working on this and struggling with it. And I said, well, let's just go back to the geodesic integrator paper, you know, the Langevin, and just do that with it, really methodically. So we follow exactly that framework for how to do it, and do, again, this approach. And magically, that method is very stable and very accurate. And we're able to do, like, these phase transitions actually quite well, which is extremely hard to do in these systems. Getting stability and pressure is not that easy. Okay, there's a lot of methods out there. In fact, there are just dozens of methods out there. Most of them are not very good, and the foundations are very poor. Like the mathematical description of how the methods are made is just a bit random. So, you know, you can actually see it forming these very structured states, and then go back. And we're actually now using that to study hysteresis with Eric. So to look at this and see how things behave. This is ongoing work. So the last thing I'm going to talk about very briefly is some steps to try to use this for stabilizing neural networks. So the idea is that when you do this, you have so the thing about neural networks is that they're very underdetermined by the data. So the parameterization is sort of very sloppy. There are lots of ways it's sloppy. There are some, as I said, symmetry groups, but they're also just very loose, and you're doing classification, very loose constraints coming from the loss function. There are actually a lot of solutions that will work. And so in that setting, it's similar to in other problems when you have, you know, underdetermined systems. It's actually more difficult than overdetermined systems to solve them. And so what we're trying to do is to find ways to constrain the systems as an alternative to sort of brute force regularizations. People typically just put on L1, L2 regularization terms, but that's, I don't think, a very great method, and it actually damages accuracy in every simulation we do. So it somehow adds something that's not related to the accuracy of the classifiers. And so one idea you can put in here is nodal spheres, okay? So basically you put constraints on so that if you just think about the planar classification problem, it's just you only allow rotation of these lines that define the boundaries of the classifier. Okay, so you don't allow them to just sort of, you know, the coefficients to vary, you know, all over the place. You're just constraining them to be rotations. Okay, so a simple idea. So that's very easy to do. But an even easier thing to do is just to make sure that you don't get any large weights. And so this is something you could call circle constraints. That's what I'm calling it. You could do this in a number of ways. So you could just sort of parameterize the weights, reparameterize them, so that you could now do your exploration in a modified domain where, you know, you work in the reals, but then you're automatically constrained to a finite interval for each of the weights, or you can just add some circles into the system. Such a simple device. So you just double the number of weights in your network. And this is the last slide. I'm just going to show you these pictures. So the first one is 2 million steps using the standard single hidden layer perceptron. And this takes a while, so if I do it like this, oh, it doesn't work at all, does it? If I do it like this, maybe I can. Didn't work. That was rubbish. Just let me see. I thought I could dangle my mouse over and make it go faster. Let's try again. Oh, no. It let me do it before, but it's not letting me do it now. Right. Okay. I'll let it run. You have to take my word for it, or we'll talk that long. But you'll see, over time, this interface will steepen in the way that I described, because there's nothing really restraining it. There's no penalty term here, no regularization term. And so eventually it steepens, and as it steepens, you also see it becomes unstable. So the dynamics of the weight training algorithm also become unstable. So there's something very interesting going on there. And you can start to see it steepening here. This one, which is done with this circle constraint technique, is just fine. It actually keeps a nice stability and a nice structure with the same width interface for millions of steps. So it's a stabilization procedure for neural network parameterization. I think it's kind of interesting, simple idea. So that's all I have on it.
Thank you very much. Questions?
Sorry, just a quick one. Why did you say that, I missed a bit, why do you say it's better to have some sort of gradient in the interface?
Well, that's a little complicated. So I don't know that I have a nice picture to show you, but have you ever seen the Rorschach test? It's a roundabout way of answering your question. You know what the ink blots? So, I think that's related to what people talk about when they talk about transferability. Okay, so somehow they say, well, what we want from a neural network is that when we train it on a related data set, we'll get good results. Okay, so if it works, we get a parameter set. We'll train on one parameter set, it will work well for related data sets. Mm-hmm. But what does it mean to be related? Okay, so you look at these Rorschach ink blobs, you might know what they mean, okay? But if you just say it like that, it doesn't tell you anything. So somehow you really need to make it precise. There's some sort of a data distribution, and then you draw your training data from this data distribution, you draw test data from the data distribution, and you look at the relationship between these. Okay, so somehow that's the transferability. Mm-hmm. And transferability has something to do with minimal complexity, because that's what we think of when we say that we have a good method, a good transferable method. It actually means it's sort of Occam's razor is being satisfied. We're using the simplest possible scheme. So I think that's the best answer I can give to your question. Somehow what I want is simple boundaries. So how do you think about the boundary? Well, I want really smooth boundaries. And so what I don't want is, so there's two kinds of smoothness you can think of here. One is you could have it, if you just look at the cross sections, the curves can be jagged, okay? And you typically see that with most of the standard classifying methods when you apply them
like in this case,
directly. Well, and that also seems to be a consequence of the breakdown here in these weights. And that's the absolute connection between those. I just don't know yet. But there seems to be a link between the smoothness in the sense of like a phase field model in terms of the interface gradients and so if you like the H1 norm of the classifier and the tendency to develop these jagged interfaces and more complicated interface structures. But yeah, why exactly?
Yeah, I had a question about this idea about having better integrators in terms of linear measure. So if you kill completely the bias by adding a metropolis hashing step, using one of these ideas, bar word or whatever, are you losing all the interest of the method, or is it?
No,
is it
it's totally
actually
reasonable. I think it's actually totally reasonable. You can add a metropolization layer
Better? It should
to
be
any of
better.
these schemes.
It should be better also because
Well, it
you
might
should
be
reject,
better.
You should reject less, no?
I think for Metropolis, you often have, of course, also computational cost, because you may need to evaluate the energy where you didn't need to do it, things like that. And also, you know, I mean, there's these issues with Metropolis in high dimensions that sometimes you actually get that you need to use smaller sets because to get a good accept ratio. So, I mean, there's some issues like that, but yeah, I mean, one should test because it's not so clear in these examples whether you would get that situation. But I think it's totally viable because what we're really doing here is a kind of a low temperature sampling, so who cares about the dynamics? We're not really that interested in the paths by which we obtain the solutions.
With the circle constraints, were you saying that these weights were sort of on a sphere or inside the ball? Which way around was it? Was it constraining that the sum of squares was 1?
All I did was add, so in the second version, the one that I showed here, all I did was add an additional auxiliary variable, which is a fake, but it's just there to make a simple algebraic constraint that I then can use to ensure that the weight itself varies between -1 and 1, or between.
And that's not showing up anywhere else, basically.
No, it's just free. So there's no.
So it means
You can random walk in that, but it's going to use that in order to solve the real problem.
Yeah, well, I was thinking that means that you can handle inequalities sort of with no extra questions and something.
Yeah, I think so. Yes. Maybe which inequalities?
As in, if you instead of wanting to have hard constraints on a problem, if you wanted inequality constraints, somehow you just add in the slack.
Oh yeah. Well, that is in a sense an inequality constraint, since I'm saying that I lie in this interval.
Yeah.
So that is.
Okay, I think it's time to thank the speaker again and have coffee.